Hello, I'm Shujaat. The title of my presentation is Application of Sparse Signal Processing to the Ultrasound Imaging. Here, I will present to you my recent work on deep learning-based beamformer for ultrasound imaging. Let's get started. Due to the non-invasive, radiation-free, and real-time acquisition features, ultrasound imaging is considered as a first choice for a variety of clinical applications, such as fetal or cardiac imaging. Before presenting my actual work, I would like to give you a brief introduction on ultrasound imaging mechanism. The basic imaging principle of ultrasound imaging is based on the time reversal, which is based on mathematical observation that the wave operator is self-adjoint. In other words, the wave operator is invariant under time transformation and the position of sources and the receivers can be swapped. For example, as shown in figure 1, in focused P mode imaging, the return echoes from individual scan lines are recorded by the receiver channel. Since the receiver measurements from multiple channels are not in phase, therefore a delay in some beamformer applies a time reversal delay to the channel measurements and combine them to form image at each scan line, as you can see in the arrows. By the way, the movie shown here is my own cardiac scan. In conventional beamforming pipeline, time delay signals are additively combined, followed by Hilbert transformation, envelope detection, and log compression steps. Despite the simplicity, large number of receiver elements are often necessary for desired quality images. However, in portable three-dimensional and ultra-fast ultrasound imaging system, there is an increasing demand for the reconstruction of high-quality images from limited number of radio frequency measurements. To solve this problem, I designed a beamforming framework for undersampled data. In proposed beamforming pipeline, the simple adder and Hilbert transformation blocks are replaced by deep convolutional neural network. Before designing a CNN or neural network for sparse subsample data, as mentioned in the first presentation, we need to know the nature of the data. In focused beam mode ultrasound imaging, the direction of each transmit event changes incrementally, so the acquired data does not change rapidly. This implies that there is some degree of skew redundancy exists in the receiver scanline coordinates, and it can be easily seen as a sparsity in the Fourier domain, as demonstrated in figure 3. Similarly, there is high correlation in the data across the depth as well. Therefore, to exploit this spatiotemporal redundancy, I use multi-line, multi-depth approach. The proposed CNN model is a multi-channel unit-like encoder-decoder neural network with skip connections. Proposed DeepBF directly processes subsample RF data to generate high-quality IQ data. Here, IQ data represents the signal after envelope detection. Extensive experimental results on in vivo and phantom data with various subsampling schemes confirm that the proposed method can effectively reduce the data rate without sacrificing the image quality. Here I show you image reconstruction result on in vivo data. From the figure 5, it can be easily seen that for all downsampling schemes, the proposed method outperformed the conventional delay in some beamformer. Note that the proposed method successfully reconstructs both the near and far field region with equal efficacy, and only minor structural details are imperceivable. This improvement in subsample data is prominent in different images. Furthermore, it is remarkable that the CNR and GCNR values are significantly improved by DeepBF. Even for the fully sampled case, for example, from 1.69 to 2.16 in CNR, and from 0.74 to 0.83 in GCNR. Here CNR is a measure of contrast between two regions, and it is defined as mean difference divided by total variance, and the GCNR is a generalized version of CNR. To confirm whether this improvement is real and not the artifact, I use phantom data. In figure 8, I compare the lateral and axial profiles through the center of anechoic cyst phantom using DEST and proposed DeepBF method. From the figure, it can be seen that under all subsampling schemes, on the boundary of the cyst, the proposed methods show sharp changes in the pixel intensity with respect to the lateral position in the images. Although the axial profiles show similar trend to the DES, the every relative shift in the pixel intensity is constant for all subsampling factors, which means there is no significant degradation in the axial resolution in subsample images. The study can be concluded as a universal deep learning-based beamformer can generate high-quality beam-mode ultrasound images from subsample measurements. The proposed method is purely a data-driven method which exploits the spatiotemporal redundancy in the RF data, which help in generating improved quality beam-mode images using fewer receiver measurements, or in other words, the sparse measurements. The proposed method improves the contrast of beam-mode images by preserving the dynamic range and structural detail of the RF signal in both the phantom and in vivo scans. Due to the large expressiveness of the deep neural network, proposed DeepBF model can effectively learn the various mapping from RF measurements and exhibit superior image quality for all subsampling rate. This super resolution effect of neural network is shown in both the phantom and in vivo images. Therefore, this method can be an important platform for RF subsample ultrasound imaging. Thank you for your attention. Now panelists will lead the discussion session.